By the end of this, you're going to have everything you need to absolutely master the topic of waves.
Before we can even think about measuring anything, we've got to speak the language of waves. So, let's get our physicist's toolkit ready.
First up, we've got wavelength, and you'll see it written as the Greek letter lambda. It's really simple. It's just the length of one complete wave. The easiest way to picture it is the distance from the very top of one wave, the crest, to the top of the next one.
Next is frequency. This just tells us how often the waves are coming. So imagine you're standing on a beach and one wave hits your feet every single second. Well, that's a frequency of 1 hertz. If 2 waves hit per second, that's 2 hertz.
And finally, wave speed. Now listen, it's a super common mistake to think the water or the string itself is flying across the room. It's not. It's the energy that's being transferred through the material. Wave speed tells us just how fast that energy is traveling.
This beautiful, simple equation. This is the golden rule that connects our 3 properties. It tells us that wave speed is just the frequency multiplied by the wavelength. Seriously, everything we do from this point on comes right back to this.
Right, let's move on to our first practical method. Let's see how we can actually use that equation with something called a ripple tank to investigate waves in water.
We project the waves onto paper so we can see them properly. But the really cool part, that's the stroboscope. It's just like a strobe light at a party that makes dancers look like they're moving in slow-mo. By matching the flashing light to the frequency of the waves, we can make the waves look like they're frozen in place, which makes them way, way easier to measure.
Think about it. Trying to measure one tiny blurry wavelength is a nightmare, right? Your measurement could be way off. But if you measure the total length of, say, 10 waves, and then divide that bigger number by 10, you slash your percentage error. Any little mistakes get averaged out, and you end up with a much more reliable, accurate result.
And here's the final step, the payoff. You take the frequency from your stroboscope, your carefully calculated average wavelength, and you just plug them into the wave equation. You've got it, the wave speed.
So that's water sorted. But what about waves in a solid? Let's switch gears and see how we can apply the same principles using a string and something called a vibration generator.
The principle here is very similar. This time, our frequency comes from a signal generator. We slowly change that frequency until we hit a sweet spot, and the string starts to resonate, creating a really clear standing wave pattern. It's a bit like pushing someone on a swing, you know? You have to push at just the right frequency to make them go higher and higher. The mass on the end, that just keeps the string pulled tight.
Okay, I need you to pay close attention here because this is a classic exam question designed to catch you out. One of those beautiful loops you see on the string, that is not a full wavelength. It's only half a wavelength. It goes from one point of no movement, a node, to the next. So to find the full wavelength, you have to measure the length of one loop and then remember to double it. Don't forget that.
Because doing the practical is one thing, but the exam isn't just about repeating a method. It's about showing you understand the limitations, and you can evaluate the results. This is how you really secure those top marks.
This slide is just packed with gold for those evaluation questions. For the ripple tank, you've got to keep the water depth constant because wave speed actually changes with depth. And watch out for reflections from the sides messing up your pattern. For the string, the tension has to stay the same.
You could easily see a 6-mark question just like this. And to ace it, you need a clear, logical method, just like we've discussed. Tell them what you'll measure, that's frequency and wavelength. Tell them how you'll measure them accurately, using the stroboscope and that measure 10 waves trick. And finally, tell them the equation you'll use to calculate the speed.
So let's just boil it all down to the absolute essentials you need to walk away with.
Know the definitions inside out. Remember why measuring multiple waves in the ripple tank is so important for accuracy. And please, I'm going to say it one more time. Don't forget that a loop on the string is only half a wavelength. And, of course, understanding your control variables is key to evaluating any experiment like a real physicist.
And the one crucial idea that ties both of these practicals together, the thing that underpins this entire topic, is, of course, the wave equation.
This is it. Wave speed equals frequency times wavelength. Learn it, understand it, be ready to use it and rearrange it. It is your most powerful tool for this whole topic.
And to finish, here's a question for you to really chew on. We figured out how to measure the wave speed, but what actually affects it? How could you adapt these experiments to investigate how changing the depth of the water, or maybe the tension in the string, changes the results? Now that's where the really interesting physics begins.